Radians are another unit for measuring angles, and they will be incredibly important if you pursue any advanced physics and/or mathematics courses. This is mainly due to the fact that, as you will be seeing throughout this video, using radians makes many calculations much simpler. Radians are defined such that pi radians is equivalent to 180 degrees. In other words, there are pi radians in a semicircle and 2 pi radians in a full circle, so a full revolution. Rearranging, we derive that 1 radian is 180 over pi degrees and 1 degree is pi over 180 radians. Thus, to convert from radians to degrees, we multiply by 180 over pi, and from degrees to radians by pi on 180. This can always be used, but a few key ones you'll want to know are pi over 2 equals 90 degrees, pi over 3 equals 60 degrees, and pi over 6 equals 30 degrees. Extending this to geometry, we can apply this to our formulas for the area of a sector and the arc length of a sector. The formula for circumference is 2 pi r, so the length of a specific arc, when we know the angle in the arc, will be the fraction of that angle in the whole circle times the circumference. In other words, theta on 2 pi times 2 pi r. This is a case where radians are useful, as our 2 pi's cancel out and we are left with r theta. Keep in mind this is only true for radians, however. For degrees, we have theta on 360, which does not cancel, although it can be simplified to theta on 180 times pi r. For area, we take the same approach. Theta on 2 pi times pi r squared simplifies to half r squared theta, where theta is in radians. Now, to extend radians to trigonometry, we will need to consider the unit circle. This is a circle with radius 1 and center at the origin. Hence, the equation of it in the xy plane is x squared plus y squared equals 1. However, if we use our SOHCAHTOA rules, we derive that sine theta equals y over 1 equals y, and cos theta equals x over 1 equals x. So any point on the unit circle can be expressed in terms of Cartesian coordinates cos theta sine theta. If we substitute this into the equation for our unit circle, we derive the very famous Pythagorean identity, sine squared theta plus cos squared theta equals 1. Now, if we consider the origin as point O and extend that to a point P, which intersects the tangent line from a point Q with coordinates 1, 0, we can geometrically define our tangent function as the distance from Q to P. This arises from the mathematical definition of tangent as the ratio of sine to cosine. In this case, cosine is equivalent to 1, so our y-coordinate is sine theta on 1, or tangent theta. Consequently, we can also define tangent as the gradient of the line OP. Now this is where it gets tricky. If we let the intersection of the vector from O with the unit circle be a point A, we see that if we rotate A around the unit circle, its x and y coordinates over time model the cosine and sine functions respectively. Consequently, we can derive trigonometric ratios. Looking at our x-coordinate modeling the cosine function, we see that it is positive in quadrant 1, negative in quadrant 2, negative in quadrant 3, and positive in quadrant 4. Our y-coordinate, or our sinusoidal function, we find to be positive in quadrant 1, positive in quadrant 2, and negative in quadrants 3 and 4. Hence, since the tangent function is the ratio of these two, it will be positive in regions 1 and 3, but negative in regions 2 and 4. If we read this out, we can label the 4 regions by SATC, where each letter indicates which function is positive, and A indicates that all of them are. To remember this, an easy acronym to use is the popular TV series Sex and the City. Also, if we look at our functions, we deduce that, as a result of the periodicity of trigonometric functions, adding 2 pi times some integer k does not change the value of our sine and cosine functions. Hence, sine theta plus k2 pi equals sine theta, and cos theta plus k2 pi equals cos theta. For tangent, we can make this even more specific. Since sine theta over cos theta is equivalent to minus sine theta over minus cos theta, and the latter occurs in region 3, we derive that tan theta plus k pi equals tan theta. There are some other identities which can be deduced through similar means. Considering our four quadrants and their signs, it can be easily seen that sine theta equals sine pi minus theta by symmetry. Similarly, it can be seen that cos theta equals cos 2 pi minus theta, and tan theta equals tan pi plus theta. For pi on 2, it can be seen from the graphs that sine pi on 2 minus theta equals cos theta, and cos pi on 2 minus theta equals sine theta. For negative angles, we must look at the functions themselves. For sine and tangent, we can see visually that they are odd functions, ergo sine minus theta equals minus sine theta, and tan minus theta equals minus tan theta. The cosine function, on the other hand, is even, so cos minus theta equals cos theta. Now we can move on to our special triangles. The first is theta equals pi on 4 radians. Hence, the other angle in the triangle must also be pi on 4, so it follows that the triangle is isosceles. In this case, solving through Pythagoras' theorem tells us that the side lengths are 1 on square root 2. Hence, the coordinates of our point A are 1 on square root 2, 1 on square root 2. So it follows that sine theta equals cos theta equals 1 on square root 2. The second case is where theta equals pi on 3 radians. If we extend the line from point A on the circle to the point with coordinates 1, 0, we obtain an isosceles triangle. However, we can deduce by trigonometry that the other two angles are also pi on 3, so it follows that the triangle is actually equilateral. Hence, the line from A to the x-axis bisects the triangle, so the side to the left of that line has length 1/2. By Pythagoras' theorem, we find the vertical line from A to the x-axis to have length square root 3 on 2. Hence we derive that cos pi on 3 equals 1/2 and sine pi on 3 equals square root 3 on 2. Consequently, by our earlier identities, we must also have cos pi on 6 equals square root 3 on 2 and sine pi on 6 equals 1/2. Now we can derive some more complex identities. I'll start off with the compound angle identities. Imagine we draw 2 points on our unit circle, one point A with corresponding angle theta 1 and one point B with corresponding angle theta 2, where theta 1 is greater than theta 2. Using our unit circle definitions, we can express the coordinates of these 2 points in terms of cosine and sine. With these, we can use the formula for the square of the distance in Cartesian coordinates to find the distance between points A and B. If we expand and simplify using our Pythagorean identity, we arrive at d squared equals 2 minus 2 bracket cos theta 1 cos theta 2 plus sine theta 1 sine theta 2 bracket. Now we can solve for d squared in another way using our law of cosines for sides r equals 1, and angle theta 1 minus theta 2. Now we obtain d squared equals 2 minus 2 cos theta 1 minus theta 2. If we equate the two and simplify, we finally arrive at cos theta 1 minus theta 2 equals cos theta 1 cos theta 2 plus sine theta 1 sine theta 2. But what if we have cos theta 1 plus theta 2? For this, we can just replace theta 2 in our original formula by minus theta 2. Using our negative angle identities, we arrive at cos theta 1 plus theta 2 equals cos theta 1 cos theta 2 minus sine theta 1 sine theta 2. To find the corresponding angle identity for sine, we use the fact that sine theta 1 plus theta 2 equals cos pi on 2 minus theta 1 minus theta 2. Substituting this into our compound angle identity for cosine, we eventually arrive at sine theta 1 plus theta 2 equals sine theta 1 cos theta 2 plus sine theta 2 cos theta 1. Replacing theta 2 by minus theta 2, we easily arrive at sine theta 1 cos theta 2 minus sine theta 2 cos theta 1. For tangent, we simply use the definition tan theta 1 plus theta 2 equals sine theta 1 plus theta 2 on cos theta 1 plus theta 2, and substitute in our formulas. If we then divide each term in the numerator and denominator by cos theta 1 cos theta 2, we arrive at our compound angle identity, tan theta 1 plus tan theta 2 divided by 1 minus tan theta 1 tan theta 2. For minus theta 2, we see that this will be given by tan theta 1 minus tan theta 2 divided by 1 plus tan theta 1 tan theta 2. Deriving the double angle identities from here is trivial. We simply set theta 1 equal to theta 2 and solve. Doing this for sine, we find sine 2 theta equals 2 sine theta cos theta. For cosine, cos 2 theta equals cos squared theta minus sine squared theta. which can be simplified using the Pythagorean identity to the two equivalent forms 2 cos squared theta minus 1 and 1 minus 2 sine squared theta. For tangent, we derive tan 2 theta equals 2 tan theta over 1 minus tan squared theta. The formulas which we derived here are all of great importance in solving geometry, trigonometry, calculus, and countless physics problems, particularly mechanics. I hope you will find use for them in all of your classes. Thank you for watching, and have a good day.